Okay, so we're talking about the extreme value theorem. And remember, it says if f of x is a continuous function on a closed interval, then f of x has both an absolute maximum, a biggest value, and an absolute min, which is a smallest value on AB. So let me just draw you an example here. This is pretty intuitive. Okay, it's pretty obvious. So let's suppose here's A, here's B. And let's suppose it looks like, well, we'll move B over just a little bit. Sorry, we'll make this be B right there. Okay, so, and we said, no, these are going to occur at a critical point or an end point. So here's a critical point right here, and that's my absolute max. And we would say, let's suppose this is 8 and this is 2. We would say there's an absolute max of 8 at x equals 2. Okay, so this is an absolute max. It's also a local max, okay? It's taller than anything around it. This one right here, this is just a local min. It's smaller than anything around it, but not the smallest point. Here's another just local max. Again, it's bigger than everything around it, but not the biggest. And right here at our end point is both a local min, but it's also an absolute min. And what this theorem says is no matter how you draw it, as long as you're closed, so you include your endpoints, and as long as it's continuous, I can trace the function without ever having to lift up my pen, then the function has both a biggest value and a smallest value. So we just want to take a minute and say, well, why continuous and why closed? So let's address continuous first. All right, so here's an example. Why continuous? Well, suppose my function isn't continuous. So suppose I have a function that looks like, just do a really simple one here, like this. Okay, here's A, here's B. It's defined everywhere. It has a smallest value. There's my absolute min. But where there should be an absolute maximum, there's a hole. So it has no absolute max. Okay? Something else that could happen if it weren't continuous, you know, you could have something where here's A and here's B, and you know, maybe you have an asymptote in the middle. And it's doing something like that. Okay, in this case, there's no absolute max and there's no absolute min. We don't have either one of them. Okay, so it has to be continuous. And again, just to guarantee it, there might be an absolute max and an absolute min if it's not continuous, but it's not guaranteed. And so then, here, why closed? Well, really it's the same idea. Okay, so if I had, say, a function and it wasn't closed, here's A, here's B, just take a line segment. We're getting closer and closer to a maximum value, but there is no biggest value. Similarly over here, we're getting closer and closer, but there's no smallest value. So again, the theorem is talking about guaranteeing it. So no absolute max or min here. So in order for you to be guaranteed it, then you have to have both the highest value, you have to be both continuous and closed.